Alright, so in this video we're going to talk about derivatives of trig functions. Now I'm going to start by just pretty much giving you these derivatives, and then we'll circle back and we'll prove a couple of them a couple different ways. But for now I'm just going to pretty much put them up on the screen and talk you through them. So the first one, the derivative of sine with respect to x is going to be cosine. The derivative of cosine with respect to x is going to be negative sine of x. So d dx of tangent of x is going to be secant squared of x. d dx of cotangent of x is going to be negative cosecant squared of x. And finally, the last two, d dx of secant with respect to x would be secant x, tangent x, and derivative with respect to x of cosecant of x would be negative cosecant x, cotangent x. Now, again, the reason why I put these on the screen hopefully wasn't to lull you to sleep, but I wanted you to see them written out in this way. There's nice patterns involved. You can see on the left, sine, tangent, and secant are all positive. On the right, cosine, cotangent, and cosecant are all negative. So all of the ones that begins with c's are all going to be negative derivatives. Another thing I'd like you to do is take a few minutes and jump onto Desmos and graph sine and cosine together. And then think back to an earlier discussion we had about how a derivative's graph predicts what the function will be doing. Remember, for derivatives positive, in that interval, the slope of your tangent lines are going to be positive. Same with negative. So I would encourage you to do this a little bit, and it really will be eye-opening to see the relationship between these trig functions. The other thing that I want to mention is that these trig derivatives, and I've said it before, they're only valid in radians, right? Calculus only works in radians. So make sure anytime you're using these things and actually having to plug numbers in, you're plugging them in radians and not degrees. So I'm going to go ahead and clear the screen now. We're going to prove the derivative of sine being cosine using the limit definition, and then from there we can apply that to some of the other ones. All right, so we're going to prove the derivative of sine with respect to x is equal to cosine of x, and we're going to do so using the limit definition. So the limit as h goes to 0 of sine of x plus h minus sine of x all over h. And this is where, in that pre-chapter handout, I had you guys write out the identity for sine of x plus h. This is where we need that. So that's sine of a sum, which would be sine x cosine h plus cosine x sine h, and then we still have our minus sine of x hanging off the edge there all over h. Once again, carry that limit notation all the way down like I've been preaching from the start. So real quick recap. Sine of a sum turns into this identity right here, and then minus sine x minus sine x. Now, I'm going to need to group a couple things together. I'm going to group this guy together with this guy. If I do that now, that's going to allow me to factor out a sine of x. All right, so if I put those two things together and I factor out a sine of x, that's going to give me a cosine of h minus 1. And then I'm still going to have this plus cosine x sine h all over h. And I don't need those parentheses there. I put an extra one in there. There we go. All right, so let me circle back again and show you what I did. Put these two together, factored out the sine. There it is. Leaves me with a cosine minus 1, and then plus cosine x sine h right there on the end. Okay? So my next step, I'm going to take the h and I'm going to go into both of these terms over here to the left and to the right. And I'm also going to distribute the limit while I do this. So this is going to be a sine x times cosine h minus 1 all over h plus the limit as h goes to 0 of cosine x sine h over h. Now, the reason why this is so important to see is because for the limit on the right, we have limit as h goes to 0. So we're treating this as a constant in the limit. The limit doesn't care about this. There's no h's in it. But when I look over here, I've got my sine h over h with h going to 0. So this whole thing goes off to 1, and therefore the overall limit would just be that cosine sitting right there. So this whole piece here, because this guy goes off to 1, that whole piece leaves us with just the cosine of x. Now, for the limit on the left, we're not quite as lucky. We still would need to go ahead and figure out what that is. So I'm going to have to move my writing over a little bit. So I need to figure out a way to now evaluate this limit. Remember, again, the sine isn't really too much of a concern to me because it doesn't have an h in it, but I have some work to do with this. And if you remember from your trig limits, the best way to go ahead and manipulate this, noting that if you plug the 0 in, you wouldn't get anywhere, right? You'd have an indeterminate form, would be to multiply the top and the bottom by the conjugate. So cosine h plus 1 over cosine h plus 1. In doing so, I'm going to have the limit as h goes to 0 sine x, and in the numerator, this would be a cosine squared minus 1. So if we multiply this guy here and this guy here, this would give us a cosine squared minus 1, which would actually give us a negative sine squared. And so that'll be a negative sine squared of h. And that's still over h with a cosine h plus 1. And then we still have this plus cosine x hanging out here as well. And so I'm just about there, but I'm about to run out of space. So I'm actually going to bring this guy all the way back around to make it a little more easy, or a little easier to read. So I'm going to have my limit as h goes to 0. And now I'm just going to divide this up so it's easier to see. I'm going to have a, let's say, sine h over h, and then a minus 1 over cosine h plus 1, and then we still have this plus cosine of x all hanging out. So that's the part of the limit. So again, I've got my sine x. I've got my, oops, I'm missing a sign, aren't I? I better put that in there. So we'll call that sine of h right there. So now I've got my sine x, I've got my negative, there's my negative. I need two sine h's, sine h, and my h cosine h plus 1 there and there. So again, I've just expanded this out into three different parts, it looks like. Now again, I've done that for a reason. I know that this guy here goes off to 1. But I also know in my denominator right here, when I plug a 0 in, cosine of 0 is 1. 1 plus 1 is 2. But when I plug the 0 into the numerator, that is 0. 0 over 2 is in fact 0. So that 0 is going to wipe out this whole piece right here as 0, leaving us with just the cosine of x. So when all's said and done, the cosine of x is the only thing left standing, hence the derivative of sine being cosine. So once again, it was just the limit definition. We needed a couple identities. We needed the sine of a sum. We also needed one of our Pythagorean identities, the fundamental identity for that matter, to come down here. But from there, it all falls apart if you separate it and individually take limits along the way. All right, so we're going to do another proof now. We're going to do the derivative with respect to x of cosecant being negative cosecant cotangent, but we're not going to approach it the same way as the last one. I would expect the derivative for sine and for cosine to be done the long way, essentially, using the cosine and sine of a sum identities. But here, now that we know the derivatives of sine and cosine, having proven one of them, the other being very similar, we can now just use the quotient rule on this. So what I see is the fact that cosecant is 1 over sine of x. And when I now do low derivative high minus high derivative low over low low, the rest should take care of itself. So we've got low derivative high minus high derivative low all over low low. So from our quotient rule, we've got low d high minus high d low over low low. And when this simplifies down, you can see that pretty much goes away. Leaves us with our negative cosine x on top and our sine squared on bottom. And if I split this apart, I would get a negative 1 over sine x times cosine x over sine x, which would leave us then the negative cosecant x cotangent x as we expected. So again, much more direct once we get past the formal proofs using the limit definition of a derivative for sine and cosine. The other 4 can be proven using the quotient rule as you just saw. So for the first example, we've got root x cosecant x plus 3, and if you're kind of thinking ahead a little bit when we do our y prime here, we know that's going to go off to a constant and the derivative therefore will be 0, so I'm not really paying much attention to it. Instead, I'm focusing primarily here, which does seem to give us a product rule where this would be the first and this would be the second. That first, just also as a reminder before diving in, the square root of x is going to be x to the 1/2. So as a power rule, it's going to be need to be seen as that. So using our product rule, we'll start with our first, which would be a 1/2 x to the negative 1/2 times the second of cosecant x plus derivative of the second, which would be negative cosecant x cotangent x back times the first, which would be that x to the 1/2. So maybe I'll mark it up here in a different color again like I have been. So this guy here would be the derivative of the first times the second plus here's the derivative of the second back times then the first. So once we have that out in place, this is again our unsimplified derivative. You can certainly simplify it from here by factoring out what you needed to, and then from there condensing it down. But we'll leave it at that for now. All right, so for our last example, dealing with trig derivatives for now, we've got a quotient rule. And if you remember the quotient rule, you've got low derivative high minus high derivative low over low low. But what I notice in that low, it looks like embedded in that I have a product itself. So in the low, this would be my first and this would be my second. So I'll need a product rule inside of a quotient rule. So let's go through this one nice and slow. So we've got our low derivative high. So the derivative of 3x would be 3. The derivative of tangent would be secant squared minus the high times the derivative of the low. So for the derivative of the low, now that's going to be itself a product rule. So derivative of the first would be 1 times the second. So we'd have a 1 times the secant x plus derivative of the second back times the first. Well, the derivative of secant is secant x tangent x back then times that x. And that whole thing now needs to be over the denominator squared. All right, so let's review this to make sure everything's in place. So we've got our low, we've got our derivative of the high minus the high and the derivative of the low. And that derivative of the low then, we could break apart again. This would be the derivative of the first times the second plus derivative of the second back times the first. And that's all over then low low. So a lot going on there, but again, this labeling and really understanding the template that the product rule and quotient rule has laid out for you should make these types of problems pretty straightforward, at least in the unsimplified world. And simplifying it, of course, is just some algebra, maybe a trig identity here or there, but for the most part, it should be pretty cut and dry.